Welcome to this presentation on Work Package 5 FPC-based Oracle as part of the Rewire Blockchain Infrastructure. In this session, we will explore the integration and innovative capabilities of Fabric Private Chain Code, FPC, within the Rewire project. Our motivation behind Rewire is to provide the necessary cryptographic primitives and trust extensions for supporting the secure lifecycle management of embedded systems. This encompasses everything from zero-touch onboarding to operational assurance and data sharing in a secure and privacy-preserving manner. This trust assessment occurs within the context of secure lifecycle management for all application-related data being exchanged. This exchange includes trust-related evidence to verify the trust state of the device. The Rewire Blockchain Infrastructure incorporates two distinct technological advancements to ensure safe and reliable system operations. The first component, called Town Crier, functions as an oracle by managing application-related data. The second component, FPC, handles attestation-related data and offers enhanced privacy assurances, trustworthy data verification and user access management. Blockchain provides a decentralized and secure platform to ensure that data verification and user access are handled transparently and securely. Immutable and auditable record of transactions. The architecture of blockchain as a distributed ledger ensures that all system transactions and data exchanges are recorded immutably and are auditable. This prevents unauthorized alterations and allows thorough verification and traceability, privacy-preserving smart contract execution. By utilizing advanced cryptographic techniques and secure enclaves, FPC ensures that smart contract execution remains confidential and protected, preserving the privacy of sensitive data and business logic from unauthorized access and examination. This approach safeguards not only the data but also the identity of the transaction. Data veracity and data filtering. Blockchain offers strong guarantees for the trustworthiness of application-related data throughout its lifecycle, incorporating AI misbehavior, access control. Blockchain supports a robust access control mechanism, regulating who has access to the data and ensuring that access is managed securely and transparently. Secure and scalable software update distribution. Blockchain facilitates the secure and scalable distribution of software updates within distributed ecosystems, which is essential for maintaining the security and functionality of embedded systems. Rewire is pioneering in combining different technologies to create an enhanced and secure oracle. Specifically, Rewire leverages the well-established SGX-based oracle, which provides the capability of integrating data processing scripts to be executed within a secure enclave. This approach ensures data veracity and filtering requirements are met before pushing data on-chain. In addition, the FPC-based oracle introduces new technology for privacy-preserving chain code execution. The SGX-based oracle provides access to a trusted execution environment, enabling the secure execution of chain code within the T. This enhances privacy guarantees by ensuring the correctness and trustworthiness of data through the underlying root of trust. The FPC-based oracle supports secure chain code execution within an enclave, ensuring that data is accessible only by authorized entities. It enhances data privacy and security through stringent access control mechanisms. FPC-based oracle allows the enforcement of trust-aware authorization and authentication based on verifiable credentials, making it a key component in the secure lifecycle management of embedded systems. In Rewire, FPC is considered an integral part of a secure oracle, combining these advanced technologies to provide unparalleled security and privacy. Fabric Private Chain Code brings several innovative capabilities to the Rewire platform, enhancing security and trust within the blockchain infrastructure. FPC ensures the integrity of the execution environment through Intel Attestation Service, providing verifiable proof of trust. This mechanism can also be integrated with other trusted third parties. FPC also employs a consensus mechanism to prevent rollback attacks. Rollback attacks occur when an attacker attempts to rewrite history by reverting the blockchain to a previous state, undermining its immutability. By preventing these attacks, FPC ensures the ledger's immutability and consistency, maintaining the integrity of the blockchain data. Moreover, it executes smart contracts within secure enclaves, protecting them against tampering and unauthorized access. This ensures that sensitive business logic and data remain confidential and secure. Last but not least, it safeguards the network by allowing only predefined nodes to run their own secure enclaves. This strategy helps to manage potential risks posed by potentially malicious nodes, contributing to the overall security of the blockchain network by reducing the attack surface that can be exploited in the case of a compromised node. FPC thus provides a robust framework for secure and trustworthy blockchain operations, leveraging advanced cryptographic techniques and trusted execution environments. This workflow focuses on storing and indexing attestation-related data. Such a workflow is based on the soft security policies described in the deliverable 5.1 section 6.2. The detailed steps of the flow are listed below. First, attestation data and its associated verifiable presentations coming from edge data sources are forwarded to the secure oracle. Then the secure oracle is responsible for checking the data veracity. For example, the VP is generated by the owner of the device, which is verified during the zero-touch onboarding phase by a valid issuer to proof of ownership and post them to the Fabric private chain code. FPC collect the attestation-related data and store them in the elastic off-chain data storage while preserving their privacy as highly sensitive data. Once the data are successfully stored, the corresponding storage pointers are returned to the FPC ledger. The FPC may also encrypt the traces with attribute-based encryption prior to storing them off-chain. In this first version, for simplicity reasons, the BSU ledger and security context broker will be used to store the data, but in the second version, the BSU will be replaced with the FPC ledger and the attestation-related evidence are stored directly from the secure oracle to the Fabric private chain code ledger. Moving on, I will give a high-level explanation of the flow for sealing a key. First of all, the client app invokes Fabric private chain code via the FPC client SDK, which retrieves the chain code's public encryption key from the enclave registry if not cached. This key encrypts the transaction proposal, including a symmetric key for encrypting the response, and identifies peers hosting the chain code. The query is sent to the FPC shim in the enclave, which decrypts it and invokes the chain code with plaintext arguments. After that, the FPC chain code processes the invocation using its logic, accessing the world state through FPC shim operations. The shim handles state data encryption, decryption and read-write operations, ensuring the data remains encrypted when stored. After execution, the result is encrypted and signed by the FPC shim, then sent back to the peer for regular Fabric endorsement. And lastly, the FPC client SDK validates the enclave endorsement by verifying the signature and state updates. It ensures the consistency of the read-write set and chain code version. Once endorsed by the peers, the transaction is sent to the orderers. The client decrypts the successful response and delivers it to the application. Let's now discuss the environmental setup for our demonstration. The Fabric private chain code is deployed within the development container provided by the Hyperledger Foundation and IBM. This environment ensures that we have all the necessary tools and configurations to effectively showcase the capabilities of FPC. Currently, we are using Fabric by default with our endmost goal to make the connection with REWIRE BSU. FPC's consensus mechanism focuses on attestation and verification of the execution environment's integrity. This approach contrasts with traditional consensus algorithms like proof of work, emphasizing the trustworthiness and security of the execution environment over computational power. In this demo, we will deploy users' chain code designed to facilitate the secure storage of attestation evidence on the ledger. This deployment highlights how FPC ensures data privacy and security, leveraging the unique properties of secure enclaves and the robust infrastructure provided by Hyperledger. With this setup, we are prepared to demonstrate the core functionalities and security features of FPC in a controlled and reliable environment. In this section, we will provide an overview of the video demonstration. The demonstration begins with the deployment of the FPC network within the development container provided by Hyperledger. This setup process differentiates from the conventional Hyperledger Fabric setup, emphasizing the unique elements introduced by FPC. Next, we orchestrate the deployment of system chain code across organizational entities. This critical step involves the creation of secure enclaves, which are essential for the subsequent deployment of user chain code. These enclaves ensure that the execution environment is both secure and trustworthy. The demo will then show the process of posting an attestation report onto the FPC blockchain. During this process, the system chain code is invoked to verify the integrity of the execution environment. The attestation evidence originates directly from the device, depicting its integrity status and thereby creating a trusted data hub for the entire service graph chain. We will also demonstrate the retrieval of the report from the ledger. Similar to the posting process, this involves invoking the system chain code to verify integrity before retrieving the attestation report. Through this video demonstration, you will see how FPC enhances security and trust within the blockchain infrastructure by leveraging attestation and secure enclave.
We commence our video demonstration by initializing the FPC network within the FPC dev container provided by Hyperledger, marking the departure from the conventional Hyperledger fabric setup. Following the addition of members and the configuration of orderers and peers, the system executes a meticulously orchestrated sequence of operations. Firstly, it orchestrates the deployment of system chain code across both organizational entities. This critical phase sees the creation of enclaves, pivotal for subsequent user chain code deployment, ensuring the robustness and security of the network. Subsequently, the script seamlessly deploys user chain code within the established enclaves across organizational boundaries. Thereafter, the system's chain code assumes the responsibility of registering these user chain code enclaves onto the ledger, facilitating future validation and verification processes. Furthermore, it's noteworthy to highlight a distinctive aspect of this implementation: the pre-registration of user within the created enclaves. This feature, while enhancing security, poses a limitation by restricting the dynamic addition of new user post-initialization. Addressing this constraint is a focal point of our future research endeavors, aiming to enable the seamless integration of new users into the network fabric beyond its initialization phase. In conclusion, the script establishes vital inter-organizational connections, culminating in the realization of a fully operational FPC network. As we move forward in the demonstration, we encounter a pivotal component, the attestation report, poised to be pushed onto the FPC ledger. It's imperative to note that this structured data is defined in deliverable 5.1. Within this JSON structure known as the attestation report, several key elements merit attention. Firstly, the task ID field denotes the nature of the verification process, in this instance, configuration integrity verification. This task identifier provides crucial contextual information for subsequent operations. Next, we have the list of access attributes, showcasing the permissions required for accessing the user's chain code. These attributes serve as the gateway to invoke the desired functionalities securely within the network. The result field carries paramount significance, offering insights into the integrity status of the system. This status report is indispensable for ensuring the trustworthiness and reliability of the entire network ecosystem. Moving on to the signature, it is meticulously crafted using the attestation key of the device. This cryptographic seal serves as a testament to the authenticity and origin of the attestation report, bolstering its credibility and verifiability. Lastly, we encounter the PKI verifier, a cryptographic key intrinsic to the FPC infrastructure. This key plays a pivotal role in verifying the signature, thereby facilitating the seamless invocation of the user's chain code. In essence, this attestation report encapsulates vital information crucial for maintaining the integrity and security of the FPC network, paving the way for seamless transactional operations. In our upcoming demo segment, we'll illustrate the process of posting the attestation report onto the FPC blockchain, followed by retrieval. While we'll provide a high-level overview of these procedures, detailed technical information can be referenced in deliverable 5.1. Here we see two terminals, one representing the FPC network initiated earlier, and the other poised for invoking user chain code functions via terminal commands. We'll commence by posting the attestation report. Observing the network terminal logs prior to invoking the user's chain code functions, we'll witness the system chain code being invoked. This invocation serves two primary purposes. Firstly, to retrieve the chain code enclave's ID, and secondly, to verify its integrity. Additionally, there will be a verification step to ensure that the invoking user possesses access to the user's chain code enclave. Upon successful invocations, the user's chain code will be invoked to submit the report into the ledger. Subsequently, when retrieving the report from the ledger, a similar process ensues. This streamlined process ensures the integrity and security of data transactions within the FPC network, laying the foundation for robust and trustworthy interactions.
Immediate next steps involve the instantiation of FPC with the REWIRE Trusted Computing Base. This includes receiving and pushing data to the FPC-based Oracle system. Additionally, benchmarking, reporting, and querying as outlined in D6.1 are essential. Moving forward, integrating FPC into various use cases is a priority. Researching and integrating the FPC-based Oracle into different scenarios will allow us to leverage its security and confidentiality features effectively. Furthermore, establishing interaction between the SGX-based Oracle and FPC-based Oracle is crucial. This interaction will be facilitated through a context broker, which will act as a server to facilitate seamless communication and coordination between the two systems. In the long term, several key initiatives will drive the evolution of our project. Firstly, in ledger management, we aim to explore methods to externalize the ledger from the enclave. This involves keeping the chain code within the enclave for heightened security while ensuring the ledger remains accessible and manageable externally. Next, dynamic user registration is a focus area. We're researching ways to eliminate the limitation of pre-registering users to enclaves during system initialization. Our goal is to enable dynamic user addition post-initialization, enhancing flexibility and scalability. Integration with the REWIRE crypto agility layer is another critical aspect. This integration will incorporate attribute-based access control and connect with verifiable credentials and presentation. Additionally, attribute-based encryption will be integrated to bolster security and access control measures. Lastly, direct interaction with town crier is on our agenda. This interaction will occur without the need for a context broker, streamlining communication channels and ensuring efficient data exchange and processing.